Hello everyone, so today we're going to be talking about total internal reflection, which is a very weird thing, and the weirdness of it is in this image. I've learned how to put some using different programs, so I put images into this thing. Very happy, a smiley face there. Now I want you to consider what's going on in that image. We can see two fish, but one of them's upside down. So this top fish is clearly, this top fish is a reflection. This is an image or a virtual image of this fish. This is the real image. This is where the real fish is. So if we sort of imagine what that must look like sort of side on, what we have is there's our water line. And we've got our person who's armed with a camera who is there. And what they can see is they can see this real fish that's here. And the reason they can see the real fish is I've got my rainbow pen. I've got the rays of light that are coming through and in a straight line from the fish to this person. All fabulous. And that is so why I can see the real fish, which makes sense. It's exactly where it is. It's in front of me. The difficulty emerges with this fish that's on the top. So I'm going to use a slightly thinner pen actually for this, so I can draw it. I've got this image of the fish, and it's up here. And if I'm seeing that fish up there, well, that must mean that what's going on here is some form of reflection. So I'm getting a ray of light that's coming up here, reflecting off, it's coming to me, and what this person is seeing is a virtual ray. So there's this image of a fish that's up here, following, of course, standard law of reflection. But actually, if you think about it, this is weird, because if there's one thing that water's pretty famous for, it's for being transparent. Okay, water is a transparent medium. Light travels through it completely fine. So why is this light reflected? Why is it not going through? Why am I able to see an image up there? If you think of what it should do is it should come up. It should then bend away from the normal and go off in sort of that direction somewhere. And I should end up with a refracted ray. That's what should happen, but instead I'm getting reflection and I'm able to see an image. And that phenomena is called total internal reflection, because I'm not getting a faint image. This is absolutely clear. That is a clear image of that fish. Okay, it's wobbly because obviously of the surface of the water, but it is a very clear image of a fish. And that means that pretty much that light, that is all being reflected downwards to give me that, because I can't even see any of the detail above the surface of the water. I've got no idea. I can't see anything from this person's point of view, because all I'm really seeing is loads of reflected light that are being struck up, and I'm getting sort of details about like the seabed. That's the seabed under it. So what's going on is essentially what I'm going to do is down here is this. This is the phenomena that is happening. A ray of light that is trying to escape. So we've got a ray of light. It's trying to escape from a more dense medium. So this is where, a sort of a high N medium into a low dense medium, low N medium, so air basically. But instead of refracting through, we're just following the law of reflection. And what I'm going to do is cut this video now, and you're going to see we'll have to go to some to a demonstration of this at work in the lab, because I want to know, when does this happen? When does this light get reflected instead of being refracted and sent through? Because that's what we're going to do to try and identify that today. Hello, year 10. So back in the lab, back with the laser, back with all the fun. And we're going to talk about one of the slightly weirder properties of light as it tries to move from one medium to another. So as before, I've got my ray of light, my laser light, which is going all the way through.
And if I ask it to go through this block here, well, yeah, this is a column of perspex. So yeah, as you can see, it goes straight through and the light ends up here on my finger, gets all the way through. That, so far, so good, so much so expected. However, something weird can happen if we're focused on what's going on inside the block and things are happening at an angle. So if I make this go slightly, what can happen if I ask it to go through? It can go through like that. But if I start asking it to do this, what we might start to see is a very strange property indeed. Now this is an example of trapping light. What we can see here is the light is coming through, we're getting a slight bending as it enters the ray of light, and it's coming here. Now this is a transparent material, like, you know, here, this is the side of this is perspex, it's completely see-through, there's nothing, you can see through this. But, oh, that's even better. What we now have is a situation where that ray of light doesn't come through this medium. What we're actually getting is reflection. We're getting there to there and there. And we're actually getting a bit of internal reflection that's going back, so we end up with that. But my hand here, none of that laser light is coming through that and hitting my hand. This is essentially a property which means that we can trap beams of light. And this is the phenomena. It's called total internal reflection, and its use in physics and engineering purposes is amazing, because if I want to send a message, well, you know, light is the fastest thing that I can use to send. Okay, it's fantastic. But the problem with sending, you know, standing somewhere and just like flashing a laser at things is that that light, I can't control where it goes once I end up with it, you know, once I sort of like let it go, just go in a straight line. But it turns out that if you trap that ray of light in a column of a certain material, you can trap it inside it, and you can bounce it, and you can make it suddenly go up to here. And this allows us to make cables that allow us to send light around and make it do different things. This property called total internal reflection. So this is a very large scale version of what we call a fiber optic cable. And this phenomena of total internal reflection can occur at very, very specific instances. And to do that, we're going to investigate that. Yeah. So here, I'm going to put a protractor on this, and I am going to use a semicircular block, like so. And I'm going to pop the semicircular block on top of this so that it's sitting on that line. Now what this means I can do is I can fire rays of light, I can angle a ray of light in at various different things. So I'm going to move that down here, and I'm going to send a ray of light through at, let's say, 20 degrees. So I'm along at 20 degrees. Now here, we come through. The reason we use a semicircular block is that I can therefore align this ray to the normal. So I'm not going to get any change in direction as it enters the block. So what I know is that this is going in at 20 degrees, it's coming down here, I would have a normal. So I'm interested in this boundary this time, not here, I'm interested here. I'm interested in what happens as this ray of light tries to pass through here and come out. And here, we've got what we normally expect to happen. We've got a refraction, and the light speeds up, bends away from the normal, and we've got an angle here that's bigger than our sort of angle here. But if we increase this angle, what happens? Well, let's go to 30 degrees. So 30 degrees, ooh, BBC News. 30 degrees, same as we normally expect. Ray of light comes in, goes straight through. We've got refraction, we're coming out. Let's go to 40 degrees. 40 degrees, coming along. Ray of light comes through. You might notice we're actually getting more light is being reflected, but again, still we've got refraction. We've still got what we would normally expect to happen coming out. But something is about to happen as we go a bit past 40 degrees. Now, about here. Suddenly, at an angle of somewhere between 40 and 45 degrees, I go from getting some light refracted. Some light is ending up on this side of the block. I move around and I end up with suddenly none. There is no light. If my finger is here, no light is now getting through this period. Should really actually have that aligned properly. 45 degrees, 50 degrees, nothing is coming through. And this is what we call, is something that happens called total internal reflection. So when our angle of incidence at this base part here, when the light is in the medium, it's trying to get out. So we're thinking about going from a more dense medium to a less dense medium. Something here, if the angle is big enough, well, none of my light gets through. Nothing here at all. The light comes in, it's reflected off, and this means that I've trapped the light. And so in building a cable to deal with this, the same thing, if I want to use a fiber optic cable, what a fiber optic cable is something where all I need to do is ensure that the ray of light never hits, is going to hit internal, it's going to bounce around inside the cable. As long as it strikes that above a certain angle, well then no light gets through. I can trap my light and I can use that to send signals. This is how many internet signals work using fiber optic cables. We can encode a message inside this light by various things of using different frequencies or flashing things on and off. So I could maybe make that a Morse code. But what I can do is I can make it go in a very different direction. And that property is something that becomes incredibly useful in industry and in various other methods, in various other places. And that's the property called total internal reflection.
Okay, so we're back at the PhET simulator, and we're going to use this for you guys to work out the critical angle, or try and measure the critical angle of the different materials. So that's the water and the glass and all the other history ones we need to. So here, because we can't move the laser sort of down, we're dealing with the ray of light is at the top, so that's the medium that we're in. And if we have sort of going from air, say, into glass, although you can get a little bit of reflection at the top, there's no way for me to get all the light reflected. There is always some going through. So what we'll do instead is we have to move that one back to being air, and let's say that we start in glass. So we'll start here. So this is sort of our equivalent, and as we move this around, what we'll find eventually, as we get certain things, we eventually hit a point where there. That is the point at which you're going from some light is reflected, is refracted through, and some is reflected, but then you hit a point where there is nothing. And that moment there is called the critical angle. So whatever this angle is, as long as we're bigger than this angle, as long as the angle of incidence is bigger than this angle, so it's down here or somewhere, we will get total internal reflection. We will not be able to see someone sort of down, someone on the outside will not see this laser light. It will bounce back on itself. If you are less than the critical angle, then you have a thing where the ray of light will travel through, or at least part of it will, and that point there. So what we're going to be doing is I'm going to do this, and as we can see, it will be different for different things. If I do it for water, it'll be a different one again. So that is a different angle to the other one. So if I go from water to glass, I find where glass, it's a sort of, so here we've got a situation where nothing comes through for glass, but for water, some is coming through. Mystery B, some is coming through. So that's this thing. So what I want you to do is to take each of the materials, so water, glass, A and B, and attempt to measure their critical angle. How? Well, I'm going to go to a custom. Let's do something like that. Well, measure it along. Find the final thing at which nothing is coming through, so it's found there. Protractor in, and you're measuring that angle. So for this one here, I'm measuring an angle of about just under 60 degrees, so about 58 degrees for this random one that I've picked. Okay, so do that for each of those in turn. Okay, so what do we have? Firstly, I have a smudge on that, so that's upsetting. So what we get is that we have some values for the critical angle for different materials. So let's take what we found for the critical angle of glass. Okay, and what you should have found that is it should have been around about 42 degrees. So 42 degrees is the critical angle, and that means that if you have a ray of light and it's coming, so here is some air and here is some glass, and that ray of light, let's have a rainbow colored ray of light, is coming in. Let's draw our normal. There's our normal. Well, it's about this angle here. It's purely about what this angle of incidence is. Okay, we're calling the angle of incidence because it's the angle at which, that's where our ray of light is going in at this angle. Okay, so it's what will happen will depend on what that value of that angle is. Okay, so for glass, okay, in the case of glass, we get an if the angle of incidence is less than 42 degrees, well, that leads to getting refraction as the ray passes through. If the angle of incidence is, however, greater than 42 degrees, then we get total internal reflection. Now, the case is often said, like, how do you draw it if the angle of incidence is equal to 42 degrees? Well, it doesn't actually do this, but the theoretically prediction should be is that the ray runs along the boundary. So we get the following sort of situations. So if I have boundary there, if I is quite shallow, so there's my normal, I'll end up with something like that. So I'll get refraction as it bends away. If, however, I've got a big angle of incidence, so much greater than 42 degrees, I get reflection. But if I get it where the ray is exactly 42 degrees, then in a lot of places what you'll see is the idea, in case it comes up in exam questions, is that it comes in and then runs along the boundary between the two things like that. So that. And that is unique for different materials. So glass has a critical angle that comes out of being about 42 degrees. Water has a different angle. Diamond has a different angle. So for diamond, it's about 24 degrees, which means that for diamond, it's quite likely that things will reflect. So this angle that you measure is called the critical angle, and that's often written as C. Okay. Now, what we can do, however, is try and see how that is related to something else that we might have measured before, because you might be aware you've done this, and different sort of like materials have different critical angles and they have different refractive indices. Okay, so there is a link between the the critical angle and the refractive index of a material, and that is found sort of as follows. We can kind of just show that it's true. Okay. If I do sine of 42, well, sine of 42 is 0.669. And I'm going to put the 1 there as well. So that's just a number. But what happens if I do 1 divided by sine of 42? Well, that is 1 over 0.6691. And if I do 1 over that number, I get 1.49, which you hopefully might remember is the refractive index of glass. So there is a relationship between the refractive index, which is n, and the critical angle of the material, which is c. And it is as follows, that refractive index is equal to 1 over sine c, the sine of the critical angle, which allows us to work sort of backwards. So we can say that, well, if we say that the refractive index of water equals 1.33, well, that means that we could therefore say that n is equal to 1 over sine of 1.33. Nope, sorry, wrong way around. Nope, that's, oops. So n equals 1 over sine c. We can rearrange that. Sine c goes up and goes down. So you get sine c is equal to 1 over 0.33. So 1 over 1.33 is 0.7519. Equals 0.7519. And what we can then do is say, okay, so I can calculate the critical angle from my refractive index by doing sine to the minus 1 of 0.7519. And I get from that 48.8 degrees, or about 49 degrees, which is what you would have measured as being the critical angle of water. And there we go. That is this sort of relationship between two things, measuring the critical angle and using that to relate to the refractive index of the material. So just sort of in summary of the two equations that we've met, you've got a refractive index equals sine of I over sine of R, and that is to do with when you've got a ray of light coming through, refracting, and then doing this kind of, so through a block. And in this, you're measuring two angles, I and R. So there's your angle of incidence, there's your angle of refraction. And that is useful for working out n because you can take lots of different values and do that repeatedly. However, we also have a relationship that n is equal to 1 over sine c, and that occurs when you have a ray of light which must be going from a more dense to a less dense medium, and it must be traveling in such a way that it comes along and hits an angle that essentially we get. So for that, it only happens at one specific angle, which means that it's not really very useful in terms of, as a practical, to try and say, here is what the value, here's what a value of n would be, because this method can only really give you one result, whereas this can give you lots, and you can work out an average and deal with those two things. And there we go. That's the refractive index and its role in various physical phenomena.